let's get started. So today we're going to, homework 2 is due this evening at 1 second before midnight, the usual. Please make sure you're doing your own work and also show your work supporting your answers. And this is on application layer. So the bulk of today, continuing on, we're going to spend our time discussing the Reliable Data Transport Protocol. And this is an abstraction in this particular textbook, Computer Networking Top-Down Approach, for understanding the semantics or the behavior that TCP engages in between the sender and the receiver endpoints. And I can say understanding TCP semantics is one of the top 10 things that you should know if you intend to be someone who chooses a career in computer networking. That's both on the design side, the diagnostic side, infrastructure side, as well as the programming side. Understanding deeply the transmission layer will actually get you a job, right, in many cases. And so this captures the nature of the interactions between the transmission layer sender and receiver endpoint, and it does so using an incremental approach. And it starts out by assuming the unreliable channel doesn't have any errors, and then over time, with different versions of this RDT protocol, Reliable Data Transport Protocol, it introduces things like error, packet loss, and things like that. And so the setup is as follows. Here we have a view of the transport layer. That's what's in the center here between these horizontal red bars. And above the transport layer is the application layer. And so the application layer communicates whether outbound or inbound with the application layer communicates inbound or outbound with the transport layer through the socket interface. And so there's a one-to-one mapping, as it were, between the so-called port number and the socket. And so the application interacts with the transport layer in two ways. On the outbound side, the application sends data or message, more correctly, to the transport layer, ultimately for delivery to the transport layer on the receiver side. And when that data gets there, that segment, inside of that segment, is stored the message data sent by the sender application. And on the receiver transport layer, it unpacks that data, that message for the application from that segment and delivers it to the correct application above. Right now, the transport layer below the transport layer is the network layer, and as we had discussed, it's the network layer's responsibility to get that segment. It wraps it up in other pieces of information, adding network layer header information, and it tries to get that packet or datagram, as it's called in the network layer, to the network layer on the other side. And so the transport layer makes use of the network layer services. So it takes its segment and it sends it to the network layer below on the sender side. And then the converse happens on the receiver side. The network layer on the receiver side gets its datagram. It unpacks from that the segment stored inside and delivers that to the transport layer above, which then delivers the message data from that segment to the application above. Okay? And so in the book, they talk about RDT send, connotes reliable data transport send, and that's the call from above, and that's going to be used to mark the event corresponding to, or identify the event corresponding to the application sending data in through the socket, right? So it's doing that send. And then the transport layer engages in a bunch of stuff, and then it calls UDT send. And so the network layer, it's unreliable, right? And so this transport layer calls unreliable data transport send. And of course, either that packet gets through or it doesn't get through. And so the transport layer on the sender side has to engage in a bunch of things, a bunch of actions, which we'll talk about. Likewise, on the receiver side, it has to engage in a bunch of actions in order to ensure this reliability. And from the standpoint of the application on the sender side, when it sends that data, it doesn't know and it shouldn't care whether or not that data had to be resent. All of that is handled by the transport layer. That's what is meant by reliable data transport. And so this UDT send below represents the call that the transport layer on the sender side makes to the network layer below it on the sender side. And it's called UDT because it stands for unreliable data transport. And so this UDT send is called by the transport layer in order to transfer a packet over what we will see in its full treatment as an unreliable channel. So then, with enough sends in this unreliable channel, at some point it's going to get through. Of course, if there's a high probability that it's going to not make its way between the sender network layer and receiver network layer, it sends it again and sends it again and sends it again until eventually one of them is going to get through. So this datagram gets through, and RDT receive is called, and this RDT receive is the event corresponding to the delivery of this datagram from the network layer on the receiver side to the transport layer on the receiver side. And so once this RDT receive is called, this transport layer on the receiver side engages in some actions we'll talk about in great detail, and then ultimately delivers, bless you, ultimately delivers that message contained inside of that segment it obtained from the network layer below. It delivers that message data to the application above, identified by the port number. Okay? All right, any questions about this? Okay, so let's unpack this. And of course, the deliver data is how you get the data in the application on the receiver. So they take an incremental approach, and the incremental approach assumes at the outset a very naive, very simple understanding of the capabilities of the network layer. Yes, it's unreliable, but they start out with the assumption, what if the network layer is reliable? And then they start to relax this assumption in increments until ultimately they have the full behavior of the network layer, and they augment the finite state machine, describing along the way what the transport layer receiver and sender endpoints are going to do. Okay, so they use a finite state machine to describe this, and a state corresponds to, you could think of it as a collection of variables, or you can think of it as a condition or a point that describes the type of behavior that a system will engage in. And so as you can imagine, when you're engaging in reliable data transport, you see something happen, and when you see something happen, you can do one of some fixed number of things. And so the alternatives that you can perform are based on a state, and the event that occurs triggering some action is denoted in the finite state machine as a set of so-called decorations on the edges. And these decorations are separated by a vertical horizontal bar. So the thing up top corresponds to the event that causes the state transition. And the thing on bottom of this decoration is the action that's taken. Now, sometimes you will see capital Greek letter lambda, right? It looks like an upside down V. And that Greek letter lambda corresponds to what's called a lambda move, right? Meaning a null operation, right? Because you also need to encode those situations where the action is to not do anything, right? Okay. Any questions about this? You've all done finite state machines and discrete math? Yeah? Okay. All right, so why don't we get started? Continuing on, the first assumption, and absolutely it's a naive assumption because it's not the case that this happens with the unreliable channel, namely the network layer, but you have to start someplace with the simple case, and then over a sequence of modifications, introduce more and more of the realistic complexities associated with the network layer. And so the unreliable channel is assumed at the outset for our RDT version 1.0 for the interaction between the transport layer, sender, and receiver behaviors. And so in this assumption, the underlying channel, namely the network layer, this UDT, is perfectly reliable. That means there are no bit errors. So no flipping of 0 bits to 1 bits or 1 bits to 0 bits, and also no packets are lost. Now, at this juncture, we should all understand or should all know that packet loss and congestion are real things, right? But this is a simplifying assumption about the quote-unquote best case because we want to make it simple to understand at a base level the behaviors of the sender and receiver endpoints for the transport layer. And so we have two separate finite state machines, right? The one on your left and the one on your right. They're very simple. They each only have a single state. The one on the left in this diagram is for the sender, and the one on the right, your right, corresponds to the behavior for the receiver. Now, sometimes, when maybe you studied finite state machines in discrete math, the start state was a double circle, or maybe the start state had like a little arrowhead coming into it. In the book, the convention is that the start state has this dotted arrow incident to it, right? So that's where you begin. So you can imagine you first run the process that implements the finite state machine for the sender, and it starts out in the state called wait for a call from above. Likewise, for the receiver, it also starts in a state when you first turn on or start the process associated with the runtime for the receiver transport layer. It starts in a state called wait for call from below. Now, it kind of makes sense, right? Because on the sender side, what is it doing? It accepts message data from the application, and then it does something to it, adds to it, and then it sends it out over the unreliable channel. So certainly in the beginning, our transport layer sender finite state machine is going to be waiting to be called from above. Essentially, that's the transport layer implementation of the socket send API call. So we start out with a sender, and it's waiting for this event RDT send. And RDT send has as a parameter, it has some data, and this is specifically the message data. An example of this is if you had an HTTP GET message in text, you call send on a socket, and you give it that string containing the formatted HTTP GET message. Okay, so the RDT send send event occurs, and it receives the message data from the application layer above, the transport layer on the sender side does. And so what does it do? Well, it creates a packet from that data, and this make packet connotes the action of creating a transport layer segment, and that transport layer segment is going to have header information like the port number associated with the socket that calls send, as well as some other pieces of information needed by the transport layer, or that's meaningful to the transport layer. So now, as a consequence of this make packet, we have a segment, right? And that's our packet that's constructed in the transport layer. And then it goes ahead and calls UDT send. It calls unreliable data send. Now, of course, well, let's think about this. Our simplifying assumption for RDT 1.0 was that the underlying unreliable transport is reliable. So that means that when you call UDT send, absolutely that packet of information is going to successfully make its way from the sender to receiver transport layer unadulterated, meaning that none of the bits get changed, and it's going to get there, meaning that that packet does not get dropped along the way. Okay, so recall we said the receiver transport layer, right, in its runtime, its finite state machine, it starts out waiting for information to come in from the network layer below. So when this RDT receive is called, that event rather is triggered, and in that event, when it gets triggered, the service routine for this event that handles it, you have a copy of that segment that's delivered to the transport layer on the receiver side from the network layer below it, right? So this RDT receive event occurs, and it contains that packet. And the first thing that the receiver transport layer does is it extracts the message data from that packet, right? So it gets a segment from the network layer below, and it extracts that message, and then it takes that message, identifies the port number from the transport layer header information, and delivers that data to the correct application above. Does that make sense? Okay, so what we see here, we have that constant cycling of this behavior. On the sender side, we RDT send, we make the packet, and then send over the unreliable channel. In this case, there's no errors on the unreliable channel, so every time you do a UDT send, it's guaranteed to get there. For this example, it gets there, and waiting is the receiver. RDT receive is triggered because that packet has now arrived at the receiver endpoint, and then it extracts the message from this segment, and it delivers that data to the correct application. Does that make sense? Any questions about this? So certainly, this is a very simplifying assumption, and in the real world, let me just pause for a second because I honestly can't remember if I hit record. I probably did, and I'm just being paranoid. Yeah, it's running. Okay. All right. Okay. So, what did I leave? Yeah. Any questions? No. All right. So this is a very simplifying assumption, and certainly one of the things that can happen when you send a packet over the wire is that packet can get corrupted, right? Take, for example, if you have copper wire, like these category 5 cables, these network cables here, they're copper wires in that. Now, if you were to take a hair dryer, I'm not saying do it, and you were to, go right up next to it, and while someone's sending data, you just turn on the hair dryer and put it near this. Well, you have a big electromagnet in a hair dryer, and you therefore have a moving or changing magnetic field. And that changing magnetic field induces what's called magnetic flux, and you can think of that as attracting the electrons in the wire, causing them to jiggle. And when you jiggle electrons, you induce current, right? And so the result of inducing that current in some conductor, namely the copper wires, is that things that are 0 bits might change to 1 bits, and things that are 1 bits might change to 0 bits. Okay, because 5 volts in a wire represents a logic 1, a Boolean 1, and 0 volts represents a Boolean 0. So if you can change the voltage by inducing currents in some wire that's carrying digital data, you can absolutely flip those bits and cause corruption in the data. So we'll take a look now at RDT 2.0, and now they introduce the idea that you can have corruption in your data. You can flip bits. Now, certainly, when we talked about the checksum, that gave us a prescription for detecting whether or not we had corruption, i.e., bit errors. And so the question then is, given this basic behavior of RDT 1.0 that assumed all sends to the network layer were reliable, how do you respond whenever you detect this corruption? Now, checksums allow us to do that. So, the thought is, what do people do in a conversation? So let me ask you, let's say, we were chatting on a cell phone and all of a sudden it was like, hello. Okay. What would you say? Can you hear me? Pardon me? Can you say that again? I didn't get that. Okay, great. So what you're doing, right, whether you knew it or not, you're acknowledging or sending a negative acknowledgement that you have received this data. Even in normal conversation, people are talking and one person is listening and he or she is going, uh-huh, 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 right? That's kind of saying, I heard what you said. I heard what you said, right? So this idea of acknowledgments is going to be another addition. And this acknowledgement is going to be sent by the receiver back in the reverse path. So this is something the receiver does, sends information, sends a packet, special packets, back to the sender. And there are two types of these special packets. One's called an acknowledgement, an ACK, A-C-K, and one is called a negative acknowledgement, NAC. And so when the receiver sends one of these two messages, it encodes, in the case of an ACK, that the receiver has successfully received the message. So the sender sends a packet, the receiver gets it successfully, the receiver transmission layer. So the receiver essentially, when it sends an ACK, it's like saying, uh-huh, okay, I understand what you're saying, right? When the receiver sends a NAC back to the sender, it's saying, can you repeat that? Beg your pardon? I didn't get that. You're breaking up, right? And so now we're going to add these two pieces of feedback, if you will, right? Every time the sender receives a message, if every time the receiver rather receives a message, if that message is not corrupted, you can detect that using the checksum. It sends back an ACK, uh-huh. If it detects that it's corrupted, which it can check using the checksum, it sends back the you're breaking up, right? And so we have these ACKs and NACKs, and now we'll go to this RDT version 2.0, where we're going to add to the finite state machines from RDT 1.0 the ability to respond both at the sender side and the receiver side to ACKs and NACKs. So to get your intuition, what happens if you're communicating and someone said, you're breaking up? What do you do? What do you do? You, pardon? You move. Yes, you could. From a message standpoint, but not a location. What would you do? So if I were giving you directions and the phone was breaking up and you didn't hear what I said, would you say something? What do you want me to repeat that? Right. And so the behavior of the sender, when the receiver gives it back this negative acknowledgement, its job now is to repeat what it said, i.e., to resend this packet. Okay. So let's take a look at the finite state machine. And so One of the things you'll notice is that there are more states, and certainly there are more edges, and there are more states and edges because you have to handle more of those cases. What happens when you get a positive acknowledgement? You receive it. What happens when you get a negative acknowledgement? You did not receive it. Ultimately, that should trigger a resend. So you'll notice here the sender finite state machine for the transmission layer on the sender side, it has two states, one called wait for call from above. That always happens because you need to get that message data from the application layer above from whatever, when someone calls the socket send. But we have another state here in the sender finite state machine, wait for ACK or NACK. So you're getting the message, you're sending, and then you're waiting for the feedback from the receiver. If we were to look at the receiver finite state machine, well, these events are a little bit more complex. Yes, you have RDT receive because that's what the receiver transmission layer uses, that event, what it triggers off of, to know when there's incoming segment from the network layer below on the receiver side. So we have the RDT receive on the receiver side, but this wait for call for below, you'll notice the event, it also adds a check for whether or not that segment that was received is corrupt, right? And of course, it would do that by calculating the checksum and comparing the calculated checksum against the checksum that's stored in the segment that it just got from the network layer below. Does that make sense? Okay, so let's take a look at this scheme and let's look at the operation for the two different cases that occur or can occur. One is that there are no bit errors, okay, and the other that there are bit errors. If there are no bit errors, that means the feedback from the receiver back to the sender is going to be an ACK. If there are errors, that means the feedback that the receiver sends back to the sender is going to be a NACK, and in response to that feedback, the sender should resend that segment, okay? All right, so let's get started. So here we have the sender finite state machine on the left, your left, and we have the receiver finite state machine on the right. So we start out with the sender finite state machine in the state called wait for a call from above. So it's just sitting there waiting for some application to call send on its socket, right? And it's going to trigger on the RDT send event. Okay. Likewise, at the same time, the process running the receiver side TCP transport layer runtime, it's going to be in a state starting out called wait for call from below, right? Because it's going to be triggered, its action is going to be triggered by the event of getting this incoming segment from the network layer below it. Okay, so we start our wait for a call from above in the transport layer sender side, and RDT send is called, if my clicker works. RDT send, let's try that again. RDT, great time for batteries to get low. All right. RDT send is event occurs. So someone has called socket send. And so in response to that, our transmission layer sender runtime, it takes that message data from the application, it constructs a packet, computes a checksum, and it stuffs that checksum it calculated into the checksum field of the transport layer header part of that packet. And so it creates a packet, including the checksum and the message data, and then it calls UDT send, the unreliable data transport send, by sending that segment to the network layer below it. Now recall in RDT 2.0, we added the assumption that's a little bit more realistic than RDT 1.0. We added the assumption that you can have bit errors, you can have corruption. 1 bits can change to 0 bits, and 0 bits can change to 1 bits. So now this UDT send occurs for this newly constructed packet, including the checksum, and it makes its way across the wire. And we're going to make the assumption for this case that you have no errors. So the event RDT receive is called, so it's going to trigger the receiver transport layer runtime to get a copy of this packet from the network layer below it. But it's not only just RDT receive, it also examines the checksum. And so it takes the checksum from the checksum field of the incoming segment it got from the network layer below, and then it calculates the checksum on that segment it just received. So it compares the calculated checksum with the stored checksum, and if they are equal, that means there's no corruption. And that's the event connoted by this not corrupt. So it receives the packet, RDT receive, and it checks the checksums match, so that means there's no corruption. So what does it do? Okay, well, it extracts the message data from that packet, and then it delivers that data to the application layer or the correct socket in the application layer above, and then it does a UDT send of an ACK. And so now with this UDT send of an ACK, the receiver transport layer is now giving feedback to the sender's transport layer to say, yes, I received this thing okay, I got it, and it was intact. It is not corrupt. So first, any questions about this? Does that make sense? So now this UDT send of the ACK goes back across the wire from the receiver back to the sender. And meanwhile, after the sender sent its packet in the forward direction to the receiver, it went into this state called wait for ACK or NACK. Now, this wait for ACK or NACK, it has two edges. One edge corresponds to it getting an ACK, and the other edge corresponds to it getting a NACK. So in this case, the receiver sent back an ACK because this packet from the sender was unadulterated. It was not corrupt. Okay, so we send that back across the wire, and RDT receive is triggered on the sender side, and also this other part of the event is ACK, right? So it is an ACK packet. So yep, it got back an acknowledgement, and it was received from the network layer below it. And so it got this ACK feedback from the receiver, the sender did. Okay, so now that edge transitions us back to wait for call from above, and now it's waiting for the next instance of an application to call socket send, triggering the event of RDT send. Does that make sense? Any questions about that? No? Now that's the case of no errors. Let's take a look what happens when there is corruption in the packet. Okay, and this is the error scenario. So again, we start out on the sender side, waiting for a call from above, waiting for some application to call send on its socket, giving it the application message data. And then likewise, at the same time, on the TCP runtime, or rather the transport layer runtime. I keep saying TCP when I mean to say transport layer, but nonetheless, the transport layer runtime on the receiver side is waiting for a call from below. So now, okay, somebody calls socket send. Maybe it's an HTTP GET message sent through a socket by a browser. And so this RDT send event is triggered. And in response, the sender runtime makes a packet, calculates a checksum, stuffs the calculated checksum in the checksum field, and then does UDT send on the unreliable channel. So then the sender transitions to waiting either for an ACK or a NACK, and this packet is in flight and eventually arrives at the receiver transmission layer. Okay, so the receiver side gets triggered. RDT receive occurs because that arrives from the network layer below it on the receiver side, the receiver endpoint, and then it checks, takes that checksum field, the sent checksum, and it recalculates that checksum from the segment and compares the two. So now it compares the two checksums, the calculated checksum against the stored checksum that came from the segment that was delivered, and it finds that they are not the same. Okay, that means that this thing was corrupted. And since it's corrupted, what does it do? Well, the event that's triggered, RDT receives, so it means it got that segment from the network layer below, and it was corrupt. Okay, so what does it do? It constructs a negative acknowledgement, a NACK, and then it calls UDT send with that NACK to give this feedback of negative acknowledgement back to the sender. Does that make sense? Any questions about this? All right. So this NACK goes across the wire, and all the while, the transmission layer runtime on the sender side is waiting either for an ACK or a NACK. So this time, the NACK arrives, and of course, because it's an arriving segment or datagram on the sender side, feedback from the receiver, RDT receive is triggered, and also this event is true is NACK because it's a negative acknowledgement. So it received some feedback, and it's that type of feedback. It's a negative acknowledgement packet. And so what does the sender do? Well, okay, it says, well, that means that the receiver did not successfully receive this packet that I sent it. So I'm going to send another copy of this packet, and it calls UDT send with another copy of this packet. Now, in order to resend this packet here, that means that the sender needs to now store a copy of the packet. And so what I didn't discuss is in the beginning, when it makes that packet and stuffs it with a checksum, it saves a copy of it, right? And if it's going to save a copy of it, that means it needs memory, right? And that's one of the resources that you need, memory resources, because you're buffering or storing these units of data, these packets, on behalf of the application layer. So the application layer has no idea what the transport layer is doing. All the application layer knows is that I send you a message and mysteriously it's guaranteed to get there. Now, underneath the covers, one of the resources that is needed by the transport layer is buffer space that it needs to store those packets because it might need to resend them. Okay? It doesn't ask the application layer, oh, can you give me another copy of that get message? No, it doesn't do that, right? It saves it itself. Okay, so when the NAC is received as feedback from the receiver, the sender resends that stored packet, right? So it calls UDT send with that stored copy of that packet. So now when it calls UDT send, unreliable data transport send, that new copy of the packet gets sent across the wire a second time. And that packet is sent across the wire, and let's assume that it's not corrupt this time. It's received at the receiver, and so it triggers the event RDT receive, right? Because it comes in from the network layer below on the receiver side. And it also checks the calculated checksum against the stored checksum. And this time it finds that they're equal to one another, meaning that the packet has not been corrupted. And so if it has not been corrupted, what does it do? It extracts that message data from that packet and delivers that message data to the correct application above as identified by the port number, and then it sends an acknowledgement back to the sender as feedback. So the sender, when it resent, it's still in the state wait for ACK or NAC. So then this ACK comes back from that second sent, and that ACK comes back across the wire as feedback to the sender from the receiver. The sender gets triggered with an RDT receive because new data came in from the receiver, and it notices or triggers the other event is ACK, means it's an ACK, an acknowledgement packet, and the response is to do nothing, but it transitions, the sender does, back to this wait for a call from above. And so one thing you'll notice here is that as long as it keeps getting NACs, it's going to keep resending, right, in this state for that self edge, if you will, in that state called wait for ACK or NAC. And so in this case, the sender, it'll resend. If it's corrupt again, gets a NAC, it'll resend. If it comes back with a NAC, it'll resend again. If it gets another NAC, it'll resend again. It'll keep resending until eventually something will get through correctly and it'll receive an ACK in response to that. Any questions about this? Does that make sense? And so one of the things that I should be able to ask you on an exam is I give you a finite state machine like this, or maybe not like this, and I'll say, okay, suppose you're the receiver in RDT 2.0. What would you do if you got a packet and the checksum didn't work out? What would you do? What would you send back if you're the receiver? So you're the receiver in RDT 2.0. You got a packet, checksum didn't work out. What do you send back? A NAC. Okay. You receive another copy, checksum didn't work out. What do you send back? Okay. You get another copy, checksum works out. What do you send back? Okay. All right. So one of the questions that I will ask you is I will give you one of the finite state machines for one of these versions of RDT, and I will present you a sequence of messages, and you'll assume the role of either the sender or receiver, and you should be able to discuss the behavior as a result of a certain sequence of messages that you get in time. Okay? All right, any questions? Does that make sense? Okay. And so certainly when we get to the transmission layer Wireshark exercise, you'll actually see this in action specifically for TCP. Okay? All right. So RDT 2.0, well, it adds feedback and it allows the sender to know if a message successfully was received by the receiver. But there's a little bit of a flaw. Let me ask you, what do you think that flaw might be? Any guesses? And it has to do with corruption, right? Yes, those can be corrupted. So if you can get corruption in one direction because it's on the same wire, well, absolutely you can get corruption in the other direction. So insofar as the packet from the sender to the receiver can get corrupted, so too can the ACK and NAC be corrupted. So that's a pretty bad flaw in these RDTs. And so what that means is that if the ACK or NAC gets corrupted, from the perspective of RDT 2.0, the sender has no idea, or it's not guaranteed to know whether or not the receiver got the packet. Because if I send you a packet and that acknowledgement was corrupted, I don't know what your feedback is. So I have no idea the status of whether or not I should resend that packet or if I can proceed to the next one. Okay? So there's a problem there. Um, so how do you handle duplicates? That's the issue. And so what happens is that if the sender decides to retransmit, the receiver can end up getting duplicates, right? And so we need to handle that particular case. And so one of the ways you deal with this idea of getting around this possible sending and receiving of duplicates is to add so-called sequence numbers. And so what a sequence number is, it's a number, right? And we know that numbers can increase, like 0, 1, 2, 3. And what this number is going to connote is the next packet that I should be getting, right? Each one now has a number stamp on it called a sequence number. Okay, and so we add sequence numbers to address this issue that ACKs and NACKs can be corrupted. And in the sender, we say, I'm sending packet number 0. Now I'm sending packet number 1. Okay, I'm going to go back to sending packet 0. I'm going to go to send packet 1. You can absolutely increment 0, 1, 2, 3, 4 and keep counting, or you could just say 0, 1, 0, 1, 0, 1. And that's the simple case that I'll present now, is this addition of sequence numbers. And the whole purpose of a sequence number is to address this issue where ACKs and NACKs can be corrupted, right? Because if you know what the next stamp is for a packet that you're going to send, you as the sender will know, okay, I sent packet 0. Did I get an ACK or a NACK? Well, I didn't get one. Well, I know it should have told me that it got 0. And if I finally get an ACK, I know that 0 was received successfully, right? Otherwise, I'm going to resend 0. Once I get an ACK and I just know I sent packet 0, I'm going to go now proceed to sending packet number 1, okay? And so you can get around this idea of corrupt ACKs and NACKs with these sequence numbers. So the packet sends, the sender rather, sends one packet with a sequence number stamped on it, and then it waits for feedback as to whether or not the receiver got it successfully. And then only then it sends the next packet, assuming the new sequence number stamped on it. Okay, and this is called RDT 2.1. And you notice here now, there are twice as many states. It's not 4 states, 2 states, it's now 4 states. And because we added this complexity of adding sequence numbers, not only do you detect if things are corrupt, you also have to check for the sequence number 0 or 1. So let's just first take a look at what the states are called. Wait for call 0 from above. So that means at time t0, the first sequence number you're going to stamp on a packet is sequence number 0. It's the 0th time you were called from above with message data from an application through a socket. So then you wait for the acknowledgement or negative acknowledgement for that 0th packet. Once you receive the acknowledgement for that 0th packet, you now wait for the next packet in sequence, which is packet number 1, is the stamp you're going to assume. So we'll see a state here, wait for call 1 from above. And you wait for call 1 from above for that next packet in the sequence of packets that you're sending. and then you don't proceed forward until you either get an acknowledgement or a negative acknowledgement. If you get a negative acknowledgement, well, you don't continue until you get an acknowledgement. Once you get an acknowledgement, you now wait for the next packet, and in this case, it alternates between 0 and 1. But what we'll see later when we talk about sliding window protocols for pipelining in TCP, we'll see that the sequence number will continue to increment. Okay? All right. So let's consider this. Now, there's no fancy animation for this. So we start out in the start state waiting for call 0 from above, and this is the sender side. The receiver side is equally as complex, but we're just going to think from the perspective only from the sender side for now. So the sender says, I'm going to send packet 0, waiting for that call from above. So RDT send is called, and what does it do? It makes a packet. Now you notice here in make packet, we're including another piece of information. We have the payload data, the message from the application above. We also have the checksum we compute, and we stuff that value into the checksum field in the transmission layer header. But we also include this 0 here, and that 0 is going to be the sequence number associated with this packet that envelops this message that we just got from the application layer above. So then it sends that packet after storing a copy of it, because again, we're going to need buffer resources, memory resources, because we might need to resend this packet in the future. So we call UDT send over the unreliable channel, and now we transition to the state where we're waiting for feedback about packet 0, right? And it does not proceed to the next packet until it gets an acknowledgement associated with packet 0. So here we're in a state called wait for ACK or NACK 0. And two things can happen. Either you take the self edge or you take the edge transitioning to the next state. You transition to the next state if you get an acknowledgement for packet sequence number 0. You take the self edge if you have a negative acknowledgement. So let's take a look first at the error case. So RDT receive is called. That means you got some feedback. You check the calculated checksum and compare that to the stored checksum, right? So you're always going to do error checking. You receive, and then one of two things can happen. You do the error checking and you find that it's corrupt, or you find that it's a negative acknowledgement, one of those two, right? So you do that, and if that condition, that event is true, what are you going to do? You're going to resend, because if it's corrupt, you can't tell if it's an ACK or a NACK. If it's a NACK and it's not corrupt, well, that means that the receiver didn't successfully receive what you sent it. In both of those cases, you're going to resend from that stored packet that you stored away when you first did that make packet. So you end up resending packet stamp 0, same checksum, same data. Does that make sense? Any questions about this? Okay. So what happens if you receive something that's not corrupt and it's an acknowledgement? Well, that's what this next transition is all about. So you receive a packet, okay, RDT received, that part of the event is true or it occurs. You check the stored checksum against the calculated checksum. They compare. So it's not corrupt, and you find that it's an acknowledgement. So you transition with a null operation that's capital lambda, and you transition now to the next state, which is waiting for a call 1 up from above. Now, call 1 from above, 1 is going to be the sequence number associated with the next packet that you're going to send. Okay? All right, so now somebody calls send again, and that could be somebody calls send for the socket, or it could be somebody sent a big video frame, and that video frame straddles 2 packets. It can't fit in a single packet. It's the same scenario. But nonetheless, RDT send is triggered with a call from above with the message data, and you make a packet. Of course, you calculate the new checksum because the data is different, and you stamp it also with a sequence number of 1. Right? And then you store this new version of the packet before doing the unreliable send, UDT send. So now that packet goes across the wire, and the sender transitions to this next state, which is waiting for the acknowledgement or negative acknowledgement associated with that packet stamped with sequence number 1. And so it will not proceed until it gets an ACK. If you get an ACK, it resends. If you get another NACK, it resends. If you get another NACK, resends. If you get 100 NACKs in a row, it'll resend 100 times, and it will only proceed when it gets an acknowledgement for that packet stamped with sequence number 1. So RDT receive is triggered as an event because it got something from the network layer below it, which is feedback from the receiver. Remember, this is the sender. It checks the stored checksum against the calculated checksum, and it's either corrupt, okay, if they don't equal one another, the stored and the calculated checksum, or it's a NAC, right? In both of those cases, it triggers the sending UDT send of a copy of that packet, which was just sent. So it's resending that stored packet stamped with sequence number 1, including its checksum. Does that make sense? Any questions about this? Okay, so then let's assume that it got an ACK and it was not corrupt. It triggers this transition, RDT receive and not corrupt. The stored checksum and the calculated checksum are equal to one another. And then is ACK, it finds an ACK packet. It has this lambda move, meaning it doesn't take an action. It just transitions to the next state, and that's waiting for the next call from above for new data. Okay, any questions about this? Okay, so that's the sender, and the sender's behavior is to send data, to create a packet, to store it, to send it, and then wait for acknowledgement. If it gets a NAC, it resends and waits for acknowledgement. If it gets another NAC, it resends and waits for acknowledgement. It only proceeds to construct the next packet once it gets acknowledgement for that packet stamp sequence number 0. Okay? All right, any questions? All right, so that's the sender. That's a bit of a mouthful, right? And I really want to focus on this in detail because understanding TCP, or rather transmission layer behavior, is very, very important. Any questions? No? All right. So let's take a look at the receiver side. Now, the receiver side might look like a bit to parse here. It's 2 states, and there's a lot of decoration on these states. But let's first, at a high level, think about what these states are doing, and then we'll unpack each of the things that can occur when you're in a certain state and look at the specific edge transitions. And so here, we start out in wait for 0 from below. It's wait for 0 from below because the first thing that our receiver is waiting for is that packet stamped with sequence number 0. And so it's receiving something, so it's going to look at its network layer and sit there waiting for the event that occurs when the network layer has new segment data available for it. So we have that start state. It waits for 0 from below, and then it waits for 1 from below. Waits for 0 from below, waits for 1 from below. Now, a bunch of things can happen if you're waiting for 0 from below. You could get packet with sequence number 1. That's not what you're waiting for, right? So that's an error condition. You could get a corrupt packet. Well, if it's corrupt, you have to respond back and say, something didn't work, right? Or you could get what you're looking for, then you proceed, right? So you'll notice here, for each of these states, specifically this wait for 0 from below, there are 3 edges, right? This edge, the first edge, that bottom edge corresponds to getting a packet out of order. You're waiting for packet with sequence number 1, sequence number 0, and you got sequence number 1, right? That's not what you want. You want 0, okay? The second edge here, that deals with corruption, right? You got a packet that's corrupted. You can't read it. You can't make sense of it. So you need to respond back appropriately. This top transition here, that means that things were successful. And what does successful mean? Successful means that it's not corrupt and it's the correct sequence number. Does that make sense? All right, and similarly for the second state. So let's unpack this and actually try it out. So you start out, you're waiting for 0 from below. Somebody calls socket send, and you construct your RDT receive state occurs, and you get this packet. You calculate your checksum, and you compare the calculated checksum with the sent checksum, and let's say they match one another, so meaning it's not corrupt. You also extract the sequence number from this packet, and you're waiting for 0, and the sequence number of the packet you just got has a stamp of 0. Okay, great. Everything is good, so what do? You extract the data from the packet, you deliver that data to the application layer above using the port number, and then you create an acknowledgement packet, and you include a checksum with that acknowledgement packet. Now, the reason you include a checksum with that acknowledgement packet is because you want the sender, remember this is the receiver, to be able to tell if that feedback has been corrupted or not, right? So you create an acknowledgement packet, including a checksum, so you can do error checking. The sender can, this is the receiver giving feedback, and then you call unreliable send to pass this ACK as feedback back to the sender. Okay, so now you transition to wait for one from below, and you notice wait for one from below is now waiting for the next packet. You just got packet with sequence number 0, so now you're waiting for packet with sequence number 1. So again, 3 things can happen. Either it's corrupt, or it's the wrong sequence number, or everything's okay. So let's take a look at the case where it's corrupt. So you're waiting for a packet stamped with sequence number 1 from below. You get a packet, RDT receive is triggered, and you check the checksum and you find that it's corrupt. Well, if it's corrupt, what do? You send back a NAC, right? That's all you can do if it's corrupt. You can't even tell if it's the right thing or not. So you construct a negative acknowledgement packet, include a checksum, so that the sender, when it gets this feedback, it can detect if it was corrupted. Okay? So you call UDT send with this NAC, including a checksum, over the wire, and now you're still waiting for one from below. So what does the receiver do? It says, get a packet. I'm waiting for one. I receive a packet. Is it corrupt? Nope. Send a NAC. Is it corrupt? No. Yes. Send a NAC. Is it corrupt? Yes. Send a NAC. Is it corrupt? Yes. Send a NAC. Okay. So that's what this first self edge represents. Okay. So the next thing is it's not corrupt, but the packet is out of order. It's not the sequence number you're waiting for. You're waiting for sequence number 1. It's the next packet in sequence, but for some reason you got packet 0. It could have been a rebroadcast. It doesn't matter why, but it's not what you're waiting for. So what happens? RDT receive event is triggered. You check the calculated checksum against the stored checksum, and you find they're equal, so there's no corruption. Wonderful. So then you take the sequence number, and you notice it's sequence number 0. It's not sequence number 1. You're waiting for 1, and you got something with sequence number 0. So what do? You send over an acknowledgement, right? You're ACKing sequence number 0, something with sequence 0, and you're just saying, hey, I must have been sent something with sequence number 0. Let me go ahead and acknowledge that. And you go back to the self edge. Now you notice here, it did not transition to waiting from 0. It made the assumption that because you got a packet with sequence number 0, somebody must have sent you something with sequence number 0. Otherwise, you wouldn't have gotten it. So let me just send an acknowledgement and continue to wait for sequence number 1 with the hopes that whoever sent this to me, or the sender that sent it to me, is going to now transition to sending me packet stamped with sequence number 1. Does that make sense? And so here, this self edge might seem a little bit wonky, right? Because you're saying, oh, you're waiting for one from below, but you're accepting this packet and you're acknowledging it. Why are you doing that? Well, it's doing that, you notice, when it finishes this action of sending the acknowledgement, it's continuing to wait for 1. It's not getting past that state. So it can still acknowledge sequence number 0 with the hopes that whoever sent sequence number 0 is now going to send sequence number 1 next if they get this acknowledgement intact. Does that make sense? Any questions about this? No questions? Okay. So let's look at that third edge. That third edge is going to be a true transition here. It's not a self edge. That's the bottom edge coming out of wait for 1 from below. So RDT receive is called, so you get this packet from the network layer below, and you check the calculated checksum, or compute the calculated checksum, and you compare that against the stored checksum, and they compare to one another. So you deem this packet as being non-corrupt, unadulterated, and you check the sequence number, and lo and behold, it is sequence number 1. So now you transition out of wait for 1 from below. You're going to transition to wait for 0 from below, but you're going to take a few actions. Now you're going to deliver this packet. And that's the difference between this self edge, the second edge, and the third edge. You'll notice here, it sends the ACK when it got the out of sequence packet, but it didn't deliver it. So that means the application layer above, it's not going to get 2 copies of packet 0, right? It's only getting 1 copy because it was delivered here, but it's still acknowledging that packet with sequence number 0. Now we get the right sequence number, packet number 1, it extracts the data, it delivers the data, and then it sends back an acknowledgement with the checksum over the unreliable channel. So you'll notice here, if you're the application layer above, packet 0 was sent. It gets delivered here on this transition. Packet 0 gets resent. It doesn't deliver it to the application layer, right? It sends back an ACK. Packet 1, the next one in sequence, arrives. It delivers it to the application. So from the perspective of the application layer above it, it got packet 0 when deliver data was called on this transition, right? When it got in order packet 0. And packet 1 was delivered on this transition when it got in order packet with sequence number 1. Does that make sense? So therein lies a really important distinction. Any questions about this? Does that make sense? So certainly this receiver for RDT 2.1, excuse me, is matched with the sender on RDT 2.1. And the whole idea of RDT 2.1 above and beyond RDT 2.0 is it acknowledges the fact, no pun intended, that ACKs and NACKs can be corrupted, right? And so you add checksums to your ACKs and NACKs, and then you can resend your ACKs and NACKs accordingly on the receiver side. Does that make sense? Okay. Let me do a time check. Wow, that was fast. All right. So sequence numbers were added to the packet, right? And that was very helpful to us. And it handled the case where you can have ACKs and NACKs get corrupted. And then we also added checksums to ACKs and NACKs. And we have two sequence numbers. Well, we have two sequence numbers because we want to know in the receiver side which thing we should be receiving. And on the sender side, if we don't get feedback from the receiver, we want to know whether we should resend or not, right? And so this was very helpful. But with these changes, we saw that the state machines got more complex. The number of states we introduced went from 2 to 4, right? And you'll find that in general. The more complexity you add in terms of error checking, the more alternative pathways there are, and that results in more states, right? But you still had this behavior of you send something, and then you do the validation of that send. You send something, and you do the validation, ACK or NACK, of that thing, right? And you're handling all the different nuanced cases that can occur. But there was a problem here. The receiver has to check if a received packet is duplicate. Now remember, if it was waiting for packet 1 and it got a packet 0, it sent an acknowledgement for that packet 0, which was out of order. Now, of course, this receiver, right, has to indicate whether it expects the 0 or the 1. The receiver can't really know if its last ACK or NACK was received at the sender. You send an ACK or NACK, and you have no idea of knowing as a sender, as a receiver, giving that feedback, you have no idea if the sender got it. So we need to do something else, right? A little bit different from this. And that something else leads to something called RDT 2.2 in the book. And with this 2.2, it removes the NACKs. And how it removes the NACKs, think about what a NACK means. A NACK means that you didn't get something that you were expecting to get. And another way of encoding a NACK is by including the sequence number in the ACK. And when you include a sequence number in the ACK, you're basically saying, I'm acknowledging the last sequence number I received successfully. So what does that mean? You're expecting sequence number 0. It's received successfully, it's not corrupt. You send an acknowledgement stamped with number 0. You receive sequence number 1, it's corrupt. You have not received it successfully. What do? You send an acknowledgement with sequence number 0, because if you get sequence number 1 and it's corrupt, you haven't successfully received it, right? So you acknowledge the last successful packet you've received. So if you send me 0, I'll say ACK 0. I was expecting 0. Great, I acknowledge 0. You send me a corrupt 1, I say, hey, I last received 0. The last one I received was 0. So you know, if you get an acknowledgement from me with 0, you know from me that the last thing I successfully received was a 0, and you can tell that's equivalent to saying a negative acknowledgement. Does that make sense? So now, this so-called NACK-free version of a protocol, it removes the ACKs altogether. And so instead of sending a NACK, the receiver sends as feedback an ACK, and that ACK includes the sequence number associated with the last successfully received packet. Does that make sense? Any questions about this? And so these so-called NAC-free protocols, it's a way of getting around this issue about NACs feedback coming back from the sender back to the, rather, it gets around this issue of NACs being lost that are returned as feedback from the receiver going back to the sender. Okay, so let's take a look at this. And in this example in the book, let me get some water here. They only give you half of the finite state machine for the sender and half for the receiver, because these finite state machines are symmetric. And this is the finite state machine for the sender. And if you want the full finite state machine for the sender, well, you're going to have another state down here called wait for ACK1, and then you're going to have another state down here to the lower right called wait for call 1 from above. So essentially, you take this fragment and you reflect it across this diagonal, and you change all the zeros to 1 if you want the full finite state machine. Okay, but nonetheless, this fragment does explain all the key elements here. We have our start state here, and you send a packet, and then you wait for an ACK as a sender. But you don't just wait for any ACK. You're waiting specifically for an ACK of 0. And so here you see, if you send a packet with a stamp of 0, you're now looking for an acknowledgement specifically that has a stamp of 0. So now the ACK is going to encode information, or has information that says, this is specifically what I'm acknowledging. I got 0 last, most successfully, right? I got 0 last. If you send it a 1 and it says I got 0 last, that means it didn't get 1 successfully. Okay? So here we have RDT send from above called, starting and wait for call 0 from above. We get our data, we create a packet, we calculate this checksum and include the checksum in the TCP segment header. We include the payload data, which is the message data from the application above. So some application is called socket send. And then we also include the sequence number, in this case, sequence number 0. We create this packet and we store it locally in the buffer in the transmission layer runtime on the sender side. And so we call this UDT send after saving off a copy, and this packet makes it across the wire. Now, of course, one of two things can happen. It's either successfully receive. What does successfully receive mean? It means that the receiver has gotten packet number 0, and it's sent back an ACK, and that ACK contains packet 0's number in it. Okay? So it's saying, I successfully got packet 0. That's what you're looking for. So either you got it or you didn't get it. One of those two. And you'll notice here, wait for ACK 0, it has two edges. One's a self edge, means it didn't get the feedback it was looking for, and one is a transition edge, and that transition edge would go to a state called wait for call 1 from above, right? It's basically a reflected version of this for packet sequence number 1. Okay, so let's look at the two transitions. Let's focus on the self edge for now. So of course, you receive some feedback. You're a sender, you receive feedback from the receiver, right? So RDT receive event is triggered. And one of two things can happen when you receive it. It could be corrupt, so that means you're checking the checksum. And if it is corrupt, okay, that's an error, and you're going to resend that packet that you saved, right? So sequence number 0 stamped packet is going to be resent. The other alternative is you receive it, and it's an acknowledgement for packet 1, right? If it's an acknowledgement for packet 1 that you got, then you say, oh, you know what? The receiver must not have gotten packet 0. Because I sent it 0 and it's giving me an ACK 1, that means it didn't get 0, right? It's ACKing the wrong thing. So I'm going to resend in both those cases. So let's look at the case where it got what it was looking for. RDT receive, okay, so a message segment was received. It's not corrupt, so the checksum, the calculated and stored checksum works out. They match. And it is an acknowledgement, and that acknowledgement has sequence number stamped 0. So that means that you got feedback from the receiver, it sent you back an acknowledgement, and it sent you back an acknowledgement for the same sequence number for the packet you just recently sent. So it proceeds now to wait for call 1 from above. And so similar, set of edges would happen, you'd have wait for call 1 from above, and then you'd have wait for ACK1, and we'd transition in similar fashion. Okay. Any questions about this? Does that make sense? So please do spend time looking at these finite state machines and going through and looking at the messages that traffic back and forth. So we'll end with this last fragment in the interest of time. It's 106, 107. And this is the receiver's finite state machine, right? Now, of course, this is just a fragment because these things are symmetric. So we have a wait for 0 from below. We also have a wait for 1 from below. So let's take a look at this wait for 0 from below. Okay, remember this is the receiver. So the receiver is waiting for incoming packets to come in from its network layer below. So we have the RDT receive, and if you're waiting for 0 from below, that means that either you get packet 0 or you don't. You get something out of order. So here we have a self edge, and this self edge says, okay, well, we'll receive something, and it's either corrupt or it has the right sequence number, right? So if it's corrupt, well, that's an error, and you're going to do the UDT send, and what it's going to send is an acknowledgement that has been saved before. And that acknowledgement that has been saved before was the acknowledgement that was created from before the edge that got you to wait for 0 from below. It's the acknowledgement of packet 1. And so if you're waiting for 0 from below, and you got sequence number 1, you say, well, I just acknowledged sequence number 1. Let me send you ACK1 because I'm telling you, here's the sequence number of the last successfully received packet. Okay. So then, of course, for this outbound edge, that's going to be an RDT receive, okay, and it's not corrupt, and you have sequence number 0, right? Would be that edge that's missing a decoration. And so that means everything was successfully received, and it's the correct sequence number 0. And so what do? You extract that message data, you deliver that data to the application layer above, and then you construct ACK0 with a checksum on this top edge that's missing its completion. And then you do the unreliable send of this ACK0, right? And then you transition to wait for 1 from below and continue in that fashion. So here on the receiver side, you do 2 things. If you receive something that's either corrupt or out of order, you resend the acknowledgement that you saved. So you need buffer space to store the ACK feedback that you send in the reverse path back to the sender. Or you proceed and you deliver that data if you receive something in order successfully. Does that make sense? Okay, any questions about this? No? All right, so we will pick up actually on Tuesday with RDT 3.0, which adds to this sequence number in the acknowledgement with error checking for corruption. Will add the full-blown treatment of reliable data transport, where we include the case where packets could be lost. And packets could be lost for one reason, and that's because there's congestion at the routers along the way. And to do so, we introduce the notion of timers. And when these timers expire, that's going to be another reason it could trigger the resending of a packet. Okay? All right, any questions about this? So please do spend the time to go through RDT 1.0, RDT 2.0, RDT 1.1, and finally RDT 2.2. Okay? All right, no questions? Any questions? All right, so we've gone over this in probably more detail than you ever wanted to hear, but really understanding how transport layers work is probably one of the top 10 skills that makes for very good network engineers. Okay? All right. So if no other questions, I will see you Tuesday. I'll end there, and we'll just end a little bit early rather than break up the next idea. All right, so I'll see you on Tuesday.